Hello, I hope you are having an amazing day. Well, this work is a collaboration between the Benemérita Universidad Autónoma de Puebla from Mexico and the Universidad de Sevilla from Spain. In this work, we're going to study charged fluids, which are systems that present challenges due to the electrical interaction between their components. In this work, we are interested in the study of particle suspensions. In particular, we want to understand the manipulation of microparticles as well as the associated phenomenology. The so-called electrokinetic phenomena that we observe in these suspensions are of interest in the technological industry, in medicine and microfluidics. In the present report, we really briefly present the theory that we have developed to understand the associated electrokinetic phenomena, and in particular to understand the phenomenon of electrorotation of conductive and semiconductor microparticles. In this presentation, we will show that these results can be useful to find the electrical and physical characteristics of microparticles as well as bacteria and cells. First, regarding the formulation, well, the manipulation of microparticles in an aqueous suspension is carried out by means of electric fields generated by electrodes powered by DC and AC currents. In particular, in electrorotation, the electrodes are powered by AC voltages with a phase differences of 90 degrees between electrodes, as shown in figure 3. These electrodes generate a rotating electric field which runs counterclockwise. This electric field produces two relevant effects. It induces an electric dipole that, when interacting with the electric field, produces an electric torque on the microparticles. See, for example, expression 3. However, since the microparticles are immense in an electrolytic solution, it also creates an electric double layer around the microparticles. Because of this, the charge of the double layer moves, causing a flow called electroosmotic flow that also produces a torque on the microparticle. Therefore, the angular speed of rotation of the microparticles is due to two effects as expressed in expression 1. The remaining expressions show the work scheme that we have developed to understand the phenomenon of electrorotation. Equation 2 allows us to find the contribution to the angular speed of rotation of the microparticles based on the polarizabilities A and B, which are obtained from solving Laplace equation, while expression 3 allows us to find the part of the angular velocity due to the electroosmotic flow, for which we solve the Navier-Stokes equation. Then the simulation, based on the aforementioned theory, we present the numerical results using the COMSOL software for different types of metallic microparticles of different shapes, such as nanorod shaped particles, prolate spheroidal, biconcave discoidal, like red blood cell shape, and short cylinder. In figure 1, we show the numerical results for the nanorods. The black belt shaped curve corresponds to the electrical torque on the induced dipole, while the red bell shaped curve corresponds to the contribution of the torque due to the electroosmotic flow over the microparticle. In table 1, it can be seen that our results for the coefficient of viscous friction obtained by means of the denominator of equation 3 coincide with the theoretical results of the draw 14 rods. Meanwhile, in the table below, we can observe how these coincide with those from theoretical results for a prolate spheroid. Then the experiment, for this, the electrorotation results are presented for metallic and semiconductor microparticles, titanium and zinc oxide, with an average size of 7 microns. The suspension is prepared with a potassium chloride electrolyte. The titanium microparticles are mixed with the potassium chloride electrolyte until an homogeneous suspension is obtained. Then this is injected into the device between the fingers that are shown in the image of the assembly. Later it is placed in a microscope slide and the electrodes are fed with voltage at an omega frequency 90 degrees out of phase. During this step, a video is taken and from this the angular speed of rotation of the microparticles is measured. Figure 4 shows a spectrum of rotation for metallic titanium particles in comparison with the experimental results. The black curve. The black curve is the numerical result obtained by means of the theory that we have developed. Please note that here a good coincidence is observed. And then regarding the discrepancy between the theoretical and experimental results, we speculate that the titanium microparticles have great surface roughness, which we have not considered. On the other hand, in Table 1, please note that experimental results in the second column of the table agree well with our numerical results, which are in the fourth column of Table 1. These correspond to the differential capacitance of the Debye-Hunkel double layer. Then regarding the experimental results for a suspension created by an electrolyte of potassium chloride and zinc oxide semiconductor spheres, the electrorotation spectrum that is measured for a conductivity of 1.5 millisiemens per meter is completely different from that of metallic particles when only a maximum is shown. On the other hand, for semiconductor spheres, a minimum and a maximum are observed. In the minimum, the semiconductor spheres are observed to rotate in the opposite direction to the applied rotating electric field, while that at the maximum, the spheres rotate in favor of the rotating electric field. We also show the electrorotation spectrum for different concentrations of potassium electrolyte solution. The shape is similar to the one shown above. Finally, we show the polarizability spectrum for semiconductor spheres obtained by the theory we have developed, and it also shows a maximum and a minimum. The inversion is due to the minus sign in equation 2. We must underline that in the case of semiconductor spheres, we have considered the presence of two electrical double layers, one inside the semiconductor sphere and one outside. The results validate that our hypothesis of two electrical double layers is actually correct. So I just want to thank you for your attention, and I'm looking forward for any comments or suggestions you may have. So thank you so much and have a great day.